everyone. In this video, we're going to look at the relationship between continuity and differentiability. So differentiability has an important graphical interpretation that's called local linearity. And local linearity means that the graph looks more and more like the tangent line as we zoom in on a point. Or even if you start with the graph of a curve, if you pick a point on that curve and zoom in on that point enough times, it is eventually going to look like a line. Okay? Now here's a picture of what we're talking about. We've got this curved function, and we picked a point and drew a tangent line through the point, and then zoomed in on that point. And notice eventually, if we zoom in enough times, you can't tell the difference between the tangent line and the curve because the curve now looks like a line. Okay. Now, what do you think? Are all continuous functions differentiable? Well, let's look at absolute value of x. Is f of x equals absolute value of x differentiable for all real numbers? Well, here we're looking at the graph, and what this diagram is showing you is that if we zoom in on the origin, or no matter how many times we zoom in on the origin, that graph is never going to look like a line. So the graph is not locally linear at x equals 0 because the corner does not disappear when we zoom in on the origin. So that means that this function is not differentiable at x equals 0. Okay, now the graph of absolute value of x is continuous, but it is not differentiable everywhere. Okay, because we just showed that it's not differentiable when x equals 0. Okay, so guys, this is leading up to an important relationship. Continuity does not imply differentiability. Okay, so just because a function is continuous does not mean it's differentiable. But if a function is differentiable, then the function is continuous. Okay, because if we know the function is differentiable, then we know that at that point it's locally linear. Okay, and then from that we know it's continuous. So, all right, so just remember, it only works one way. All right, so this leads into, okay, when does a derivative fail to exist? Well, we already looked at this first example with the absolute value of x. So the derivative fails to exist at a sharp corner. Okay, and again, absolute value of x is an example. At a cusp, which is just a special type of corner. Here's an example. This function is x to the 2/3, and so it has a cusp at the origin. At a vertical tangent line, because remember the slope of a vertical line is undefined, and the derivative is slope of the tangent line. So if the tangent line is vertical, then the derivative is undefined. Here's an example. Cubed root of x has a vertical tangent line and x equals 0, right there. And you guys, I'll show you algebraically, if you were to try to find the derivative at 0, so here I'm just going to use power rule. If I try to plug in 0, I'm going to keep that f prime of x. So here's f prime of 0. We're going to end up with 1 over 0, which is undefined. So, you know, even algebraically, if you attempted to find the derivative where there's a vertical tangent line, you're going to come up with a value that's undefined. So, okay. Our fourth case or condition where a derivative fails to exist is at a discontinuity. Now Now this would be at any discontinuity. Okay, so that would include a point discontinuity, which remember is a hole in the graph, an infinite discontinuity, which remember is a VA, or a jump discontinuity. Okay, so again, the derivative fails to exist at any of our three discontinuities. The example you're looking at, this is a piecewise function. There is a jump in the graph when x equals 0. So this function is not differentiable when x equals 0. Okay. So here's an example. We're given 4 different graphs, and we want to state with reason the numbers at which f is not differentiable. So again, we're just looking for these 4 things: corner, cusp, vertical tangent line, or a discontinuity. Okay, so in our first graph, well, we have a sharp corner when x equals -4. And we also have a jump discontinuity when x equals 0. All right, on graph number 2, it looks like we have a vertical tangent line when x equals 0. And then we have a cusp when x equals 3. Okay, in our third graph, okay, now, this graph actually has a vertical tangent line when x equals -1. And I can tell you guys, these are a little bit harder to see in the graph. So the good news is, usually in the problems that you're given, they will tell you the location of a vertical tangent line because they're just harder to see in the graph. Okay, and then we also have a sharp corner when x equals 4. I'd probably call this one a cusp, but it's okay if you use corner or cusp. Okay, let's look at our fourth graph. So it looks like at x equals -1, we have a jump discontinuity, and then at x equals 2, we have a corner or cusp. All right, so these are all the values where these functions are not differentiable. And why? Okay, now let's get into this algebraically. In order for a function to be differentiable at a value of x, then 2 things must be true. Number 1, the function must be continuous. Okay, and then number two goes back to the original meaning or definition of the derivative. Okay, so remember, a derivative is a limit. Now, we learned several variations of the definition of the derivative. I think I'm just going to use the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so this limit has to exist. Well, this is a two-sided limit. So what has to be true for a two-sided limit to exist? I hope you are saying the one-sided limits have to exist and equal each other. Okay, so what are we saying here? We are saying that because both of these limits represent derivatives, so we're saying the derivative from the left has to equal the derivative from the right. So you can interpret these limits into that statement, into those statements. Okay, the derivative from the left has to equal the derivative from the right. Okay. Or you could also, instead of derivative, you could use slope. The slope from the left has to equal the slope from the right, because derivative is slope, okay? More specifically, slope at a point, but. All right, so you guys, let's look at this example. Consider the function g of x. Is g of x differentiable at x equals 3? Show the complete analysis. All right, so you guys, the first thing that you want to do is show that the function is continuous. So that means we got to go back to our definition of continuity. I'm just going to put a question mark. Okay, so remember our 3 steps for continuity. The function has to be defined at 3. So find g of 3. To find g of 3, I would plug into square root of x plus 1. Okay, that's going to equal square root of 4, which is going to equal 2. All right, number 2, the limit as x approaches 3 has to exist. Since 3 is a cutoff point, we got to evaluate on one-sided limits. So let's start with the limit from the left. So again, in this case, we're looking for where x is less than 3. We are going to plug into that square root. And that's going to equal 2. Okay, the limit from the right. This would be where x is greater than 3. So we're going to plug into 5 minus x. That also equals 2. Notice we got the same answer for all 3. So we do know that g of x is continuous at x equals 3 because g of 3 equals the limit as x approaches 3. Okay, so no more question mark. We know the function's continuous at 3. All right, that means we can keep going. Now, let's say you went through your 3 tests of continuity and you established that the function is not continuous, then you could stop right there. Because if the function is not continuous, then it is not differentiable at that point. Okay? All right, now let's check differentiability. Okay, so to check differentiability, we need to find the derivative of this piecewise function. Okay, so to do that, you just find the derivative of each piece. Okay? Now, the derivative of square root of x plus 1, we would make that x plus 1 to the 1/2. We would use chain rule. Okay, and then we could rewrite that as 1 over 2 times the square root of x plus 1. Okay, now, keep your inequalities the same, but here's something. Initially, when I write this piecewise function, I'm only going to set up my inequality using less than, because I don't want to say or equal to unless I know for sure that the function is differentiable, you know, at 0 or at 3, okay? So to be on the safe side, we'll just say less than. Okay, then find the derivative of 5 minus x. Well, that's easy. That's just -1. And again, we're going to write our inequality, but don't put the or equal to unless we know for sure that the derivative exists at that point. But we don't, because that's what we're trying to figure out. Okay. Now, we found our derivative of our piecewise function. So now we just have to make sure that the derivative from the left is equal to the derivative from the right. Okay, so we're just going to find the limit as x approaches 3 from the left. Okay, using, oh, and this would be g prime. Sorry, guys, I should put a prime symbol there. Using g prime. Okay, so I'm going to plug into the 1 over 2 times the square root of x plus 1, but I'm going to plug in 3 for x, and I'm going to end up with 1/4. derivative from the right of g prime. Well, we know what that equals. That equals -1. Okay, now notice what happened. We got two different values. So that means the derivative from the left does not equal the derivative from the right. So this function is not differentiable at x equals 3. Okay, so what's the main idea here? To prove that the function was differentiable at 3, we first had to figure out if it was continuous at 3. We established that the function is continuous at 3, so then we just had to make sure that the derivative from the left equals the derivative from the right. But in this case, they were not equal, so we know the function is not differentiable at x equals 3. So you guys, what's happening here is if it's continuous but not differentiable, then there's got to be like a corner or cusp in the graph at 3. Okay, now let's look at this last example. This one's a little different. For what values of a and b will the function below be differentiable at x equals 1? Okay, so again, we're given this piecewise function. You guys, you've dealt with questions like this with continuity, you know, with questions that say, find the value of a that makes the function continuous. Okay, this one is similar, except that we're finding two unknowns, a and b. And, you know, we're finding the values of a and b that make the function differentiable. But remember, in order for the function to be differentiable, it has to be continuous. All right, so in this case, we're going to set up two different equations, one based on continuity and one based on differentiability. Okay, so the equation based on continuity, we're going to do what we've always done on these type of questions. Okay, both of these expressions are polynomials, and remember, polynomials are continuous. You know, so the only place it might not be continuous is at 1. So we're going to plug in 1 for x, and then set the pieces equal to each other. Okay, so we'll have 3 times a plus 2 times b plus 1 equals a minus 4b minus 3. Okay, so this is our equation based on continuity. Now, I'm going to go ahead and rewrite this equation. I'm going to get the a and the b's on one side. So I'm going to subtract the 1a from the 3a to get 2a. And I'm going to add the 4b to the 2b to get 6b. Okay, but then I'm going to subtract the 1 from the -3 to get -4. And you'll understand why I did that in a little bit. Okay, now our second equation is going to be based on differentiability. Okay, so that means we got to find the derivative of this thing. So again, you just set it up as a piecewise, you just find the derivative of each piece, and we just have to do power rule, so we'll end up with 6a times x plus 2 times b. Okay, that would be for x less than 1. And then we're going to have 4ax cubed minus 8bx minus 3 for x greater than 1. Okay, and then we're going to do a similar thing. We're going to plug in 1 for x and set the pieces equal to each other. So if I plug in 1 for x, I'm going to have 6a plus 2b equals 4a minus 8b minus 3. Okay, and now I'm going to do a similar thing. I'm going to subtract the 4a from the 6a to get 2a. I'm going to add 8b to the 2b to get 10b. And I'm going to leave that set equal to -3. Okay, now why did I do that? Because you have to then put the two equations together in a system of equations. system is called elimination. And so this is where you line all your variables up vertically. And then the goal is to add straight down, but you want to eliminate one of the variables. So if I add straight down right now, neither of the variables are going to be eliminated. But what I could do is I could multiply whichever equation you want to multiply. I will just take the top one. Let's say I multiply this top equation by -1. Now if I add straight down, the two a's are going to cancel, and I'm going to end up with 4b equals 1. And then I can solve for b just divided by 4. And then to solve for a, you just have to pick either of the original equations, and we're going to plug in for b, and then we can solve for a. Okay, 10 times 1/4, if I simplify that, will end up being 5/2. And so I'm going to have to subtract the 5/2. Okay, I'm going to find a common denominator. Okay, so that's going to give me -11/2. And then I'm just going to multiply by 1/2. And we'll get a equals -11/4. All right, so we did it. We found a and b. That will make the function differentiable at x equals 1. Okay, so anyway, you guys, that's the process. You set up one equation based on continuity. You set up a second equation based on differentiability. And then you're left with a system of equations, and then you just solve the system. All right, you guys, that concludes the video. So thank you for watching, and have a good night.